My name is Callie Cole. I'm an associate professor of chemistry here at Fort Lewis. And today I'm going to talk a little bit about a chemical analysis technique called mass spectrometry. Perhaps in the past 24 hours on your news feed, you read about this Russian figure skater who received a 4-year ban from the Olympics, and it got a gold medal for Team USA. Perhaps that's as far as you got. The core of this story is actually the mass spectrometric measurement of trimetazidine in her urine. So mass spectrometry is used to quantify various molecules and atoms in samples of all kinds. So before I get into the nitty-gritty, I wanted to just go through some examples of where mass spec is used. Perhaps some of those situations apply to you. Weed. We're in Colorado. Maybe you've had an edible or something. If you have, I bet you were thankful that you knew the THC content of that edible, and you could dial your experience. That's because mass spectrometry was used to quantify the amount of cannabinoids in that edible. Maybe you've taken a pharmaceutical product at some point in your life. Mass spectrometry is very involved in studying antibodies and proteins involved in various diseases. So pharmaceutical research relies heavily on mass spectrometry. Maybe you've been in the doctor's office and you've had a urine sample taken, a blood sample taken, and that sample was taken to a clinical laboratory where mass spectrometry was used to look for biomarkers of disease or other components of your sample to determine your health. Maybe you've been in the airport. Maybe, if you're lucky enough, you're pulled aside and your bag was swabbed to look for trace explosives or other controlled substances. This has happened to me, and I actually got to see the mass spectrum show up on the computer, and I wondered if the person knew what it was. But I didn't continue the conversation because I wanted that experience to end as quickly as possible. This is probably the most universal one. Like, if you've consumed Durango City water today, there has been someone running a mass spectrometer looking for trace contaminants in that water and making sure that it follows EPA guidelines so that we're all safe. We can drink water that doesn't have excess lead in it. There are more examples. This is just like a bunch that came to my mind. Some of my favorite examples aren't everyday. They're more space. If you know me, you know that I like space things. So we've been sending mass spectrometers to space for decades to measure the chemical constituents of planetary atmospheres, comets, you name it. This is the Cassini mission. We sent it through the atmosphere of Saturn and through the atmosphere of Saturn's moon Titan. And we're able to see things like methane, water vapor, complex and simple organics. It's really cool to watch specific moons like Titan because their atmosphere is really similar to the early Earth's atmosphere before the rise of oxygen. So we're kind of watching it like a really slow movie to see when aliens show up. The Rosetta mission by the European Space Agency successfully landed a probe on a moving comet. And if you can see here on the right, it says, the lander must attach itself to the nucleus of a comet traveling through space at more than 130,000 kilometers per hour. So it was quite a feat. And speaking of feet, the feet of that lander had little screws that were supposed to screw into the surface of the comet, but it was such a difficult landing that it kind of bounced and rolled for a while and eventually landed in a little crevice, but we got mass spectrometric data. Even with that rough landing, there was a mass spectrometer on here, and so we have information about the chemical constituents of comets. We've been sending mass spectrometers to Mars since the 1970s to measure the chemistry and geology of the Martian surface. This is the Curiosity rover that's currently up there, and later in the talk, I'll talk about some more rovers with mass specs that we're going to send up there too. So I wanted to start the talk with that in case I feel like most of you kind of know what mass spec is because maybe I know you or I'm giving you extra credit in my class to be here. But if you didn't, maybe one of those applied to you in your life, and you're like, okay, this is a useful technique. So I'd like to go through 4 little parts of this talk today. I'd like to start by giving some origin or background story for how mass spectrometry was developed, give you a brief overview of how it works, and then talk about how that is integrated into my research story. I've ended up using mass spectrometry at almost every single stage in my education, and that wasn't purposeful. It was because it just showed up, and it was the technique that did the job. So it's a pretty good one. At the end, I'd like to talk about some current/future applications for the technique. So let's go to the origin story. How did it all begin? With an old white guy, of course, in 1897, J.J. Thomson. J.J. Thomson was trying to understand what a cathode ray was in the late 1800s. Maybe you've heard the term cathode ray, maybe you haven't. I've got a cathode ray tube up here, quite similar to what J.J. Thomson had. Kudos to Dr. Grubb for finding it in a back closet in chemistry hall. What we have here is 2 electrodes and then an evacuated glass tube. And I'm going to go ahead and just plug this in, just 6,000 volts. Try not to electrocute myself. And then go ahead and turn the lights down if you would. So perhaps you see a light beam. A beam originated from the cathode. So the cathode is over here, hence the term cathode ray. At the time in the late 1800s, J.J. Thomson and his pals did not know what this was made of. So they were trying to understand its components and started introducing various fields, like magnetic fields and electric fields, to see how it responded. So I have a magnet here, and I'm just going to reenact an experiment. I think I have a black slide to make it darker in here. Cool. So yeah, just check this out. I'm basically going to take a magnet and bring it close to this cathode ray, see what happens. Looks like it's bending. And then I'm going to flip the magnet, introduce the opposite pole. I don't know if you can see that okay, but I'm able to bend the cathode ray with a magnet. I could do this all day. When J.J. Thomson did this, he then started experimenting with electric fields, positively and negatively charged. And he discovered that this cathode ray was repelled by negatively charged electric fields and attracted to positively charged ones, indicating that it's made up of negatively charged particles. Okay, you can bring up the lights. So J.J. Thomson discovered that this cathode ray was made of negatively charged particles. It turns out that those particles are called electrons, and he discovered them, so he got the Nobel Prize. Kudos. He didn't stop there, though. Once he had this experiment set up, and he knew that the cathode ray was simply a beam of electrons, he started to ask questions like, what would that beam of electrons do if I introduced specific substances, like hydrogen gas, helium gas, neon gas? So if I filled up this glass tube with neon gas, we know nowadays that those neutral neon atoms might interact with that electron beam and become ionized, forming like neon cations by losing an electron. And it turns out that just like the charged electron, you can also control the trajectories of charged ions with introduced magnetic and electric fields. So that was J.J. Thomson's next series of experiments that took him to the year 1913, when he published the very first mass spectrum, which is a photographic plate that shows the arced trajectories of various substances that were in his setup here. So he had mercury, he had carbon dioxide, carbon monoxide, and neon gas. I'm just gonna zoom in on the neon part. It's kind of granular here, but you can see it's kind of smeared right there. That smear was the discovery of non-radioactive isotopes. So instead of just one mark on the photographic plate, which is what he expected for neon, he got 2. In fact, there's more than 2 isotopes of neon. This is really low res. It's like a photographic plate and someone trying to arc ions, right? But what he really discovered here was that you can control the trajectories of charged species by introducing fields, and this was the birth of mass spectrometry. Also, it was the discovery of non-radioactive isotopes, which led to all sorts of things, like if you look at the periodic table And if you've ever looked at those numbers at the bottom of the element, like platinum 195.085, that number is the weighted average of all the known naturally occurring isotopes of that element. And we wouldn't know anything about the isotopes or their mass if it wasn't for J.J. Thomson and mass spectrometry. Just like every scientific advancement, and maybe not everyone, but everyone I've ever heard of, humans tend to use them for violence, unfortunately. And mass spectrometry is no different. This is a picture of the magnetic sector mass spectrometer that was developed by Ernest Lawrence to separate isotopes of uranium, specifically gathering the uranium-235 necessary for the little boy bomb in World War II. So, yes, I had to go to a dark place to explain that scientific discoveries are fascinating and dark sometimes. A more fascinating discovery related to isotopes and mass spectrometry is that a meteorite taken out of this crater, which is just outside of Winslow, Arizona, was used by Dr. Claire Patterson to determine the age of the Earth. Perhaps you've heard the term isotope in terms of dating, like carbon dating, lead dating. When we determine the ratio of isotopes in a sample, we can determine the age of that sample. Using lead dating and mass spectrometry, Dr. Claire Patterson determined that the Earth is 4.5 billion years old based on a mass spectrometric experiment on a meteorite in this crater. So that's sort of the origin story. I just told a couple historical stories, but you can imagine now that we know we can control the trajectory of charged things based on their masses and their charges, we can figure out what's in a sample, we can date it, we can also make bombs with it, unfortunately. So how exactly does it work? You've seen a very rudimentary example, but let me show you some modern mass spec layouts. So this is J.J. Thomson, one of his original layouts. You have an anode and a cathode that generate an electron beam, and then you have these negative plate, positive plate to control its trajectory. And as I said, electrons, negatively charged, so they're drawn to the positive plate. Since then, the experiment has changed a bit, but that electron beam is still present. We call it electron ionization. It's the most common ionization source available. And so here's an example of a modern mass spec. It's called a magnetic sector. We basically have a sample enter from the left. We have an electron gun, which is just an electron beam, just like the original cathode ray. And then that causes ionization. And then we can use electric fields, and in this case, magnetic fields, to control the trajectory of those ions. As you might imagine, a more massive ion will require a stronger magnetic field to arc it to the detector than a lighter ion. So we can tune the magnetic field to look through all of the different masses and charges of ions in a sample and basically get a full profile of that sample. Magnetic sector is a pretty simple one. Quadrupole is a little bit more complicated, but it's the same principle. Now we have 4 metal poles that we're applying oscillating potentials to, and some ions, based on their mass to charge, will make it through to the detector, and we can tune that voltage to eliminate ions that we aren't interested in studying. So we can monitor samples, we can look at all the ions, and we can choose specific ions. This background slide I've been using for the outline of this talk is a cross-section of a quadrupole mass spectrometer that shows a lot of the ion trajectories. There are so many. I'm going to stop after this one, but I want you to know there's Orbitraps, time of flights, FTICRs. There's so many types of mass specs that I teach it for hours in my classes. Some of you have taken. But this ion trap is a cool layout. Instead of the quadrupole with 4 poles, we now just have 2 metal end caps and then a donut electrode in the middle. And again, we're applying different voltages to attract and repel charged particles. And we can trap ions for up to days at a time. We can introduce reactants to do reactions in there, and then add a frequency, a resonant frequency with specific ions of specific masses and charges to detect them when we're good and ready to. This is just a commercial video I took from YouTube. The company Bruker produces this gas chromatograph mass spectrometer. So the gas chromatograph piece is on the far left, the mass spectrometer is on the right, and we're just gonna zoom in on it and see what a modern mass spec looks like. We stack a lot of these together. So I'm gonna narrate. There are some aspects that are similar to J.J. Thomson's setup. So here's our sample in the gas phase entering into the left, and this is an electron beam coming down from the top. Those electrons ionize the atoms and molecules, and as soon as those atoms and molecules have a charge, they are drawn in via the attractive voltages in this hexapole, which is the same as a quadrupole except has 2 more poles. And that kind of helps guide the ions through. Now we're in a quadrupole, and you can see some colored ions are removed, little pink ones. Some of those massive charges are being selected, the green ones. So it's a hexapole, then a quadrupole. Next, we're gonna enter a magnetic sector mass spectrometer, and you can see there's some just going straight ahead. Those are neutral species. So whenever you introduce a curve, it helps eliminate neutral species and keep ions only. This is really fun. We can also introduce a collision partner. So helium, nitrogen, some inert gas, we can insert that and cause collisions purposefully to break molecules apart so we can see their molecular constituents and figure out what structure they were. Once we have those broken ion fragments of a molecule, we can select specific fragments using another quadrupole before they hit what's called an electron multiplier detector. Wow. So yeah, modern mass specs, is it over-engineered? I don't know, I'm not gonna answer that question. I'm just gonna leave that. It's really fun for a scientist to be able to do collision experiments and like understand every single molecule that's in their sample, right? So overall layout of a mass spectrometry experiment, you take your sample, it could be gas, liquid, or solid. We just need to make sure that it's vaporized. So you might have to heat it, you might have to spray it. Ionize it somehow. The most common way to ionize something, introduce a beam of electrons, right? As soon as it's ionized and it has a charge, we can then introduce electric fields and magnetic fields to separate everything in the sample based on its mass and charge. Finally, let's use a detector to observe it. Electron multiplier is the most common detector. So this is what a mass spectrum looks like today, a little bit different than the original photographic plate that J.J. Thomson had, but it still does the same thing. We've got the signal intensity on the y-axis, and we've got the mass to charge ratio of various ions on the x-axis, and this is just an example of the separation of 4 of the isotopes of lead, and that intensity of signal is directly proportional to the quantity of that species in a sample. So we can use a mass spectrum to immediately say, there's a lot of this one and less of that one, right? We can get quantitative info. That was a pretty fast crash course, but that's how it works. We're controlling the trajectories of charged things and separating them. What does this have to do with me? I like to spend as much of the talk as possible not talking about me for the exact reason Christine said. She's like, faculty are uncomfortable talking about themselves. I'm like, yep, that's me, but here we go. Let's start with a picture of me with a mullet, because my mom gave me a mullet haircut my whole childhood until I was old enough to like make it stop. Anyway, this is me, and this is my twin brother, Ben. My dad worked for the Idaho Fish and Game growing up, and he took us to work with him because it's cheaper than childcare. And we banded ducks together. And if you don't know what duck banding is, it's where you put a little like metal bracelet on a little duck's leg, and it has a number on it, and you can use that to measure where they go, like their migratory patterns. So we'd have a little trap on a lake, and my dad would do work stuff, and then he would hand us the duck, and then I got the joy of like tossing the duck and watching it like flap away to its freedom. So that was my first time like doing science, I guess, and I would say that's a privilege because it was just really weird and fun, which is so much better than having like an intimidating first experience with science. I was like, this is neat. Get to toss ducks in the air. My grandma, Lois, she's gonna be 98 in May. She's still with us, being awesome, being like the coolest grandma ever. Lois taught chemistry, biology, and physics in various rural schools in Nebraska from like the 50s to the 80s. And she got National Science Foundation funding for her work. She worked with NASA. Like when you walk through her house and you just like look at the walls, there's all sorts of fascinating things, including things that indicate she's worked directly with NASA. My grandma's high school student and her designed a project looking at the germination of seeds in zero-G environments, and NASA agreed to launch it in their Skylab experiment in 1973, and they invited her and her high school student to go watch the launch. It's like the coolest grandma ever. I will never attain her coolness, but anyway, I can try. So yeah, in my family, I had like direct scientific mentors, so I'm so grateful for that. And also in my educational career, I had fantastic mentors in high school. Shout out to Woody Annan at Sandpoint High School. He's just an absolute like weirdo in the best way possible. Every single day was just unexpected. This is like a candid photo of him like teaching a class, you know? So he made chemistry just fun and strange, and it made me want to come every day and to figure out what's going on. Chris Palmer was my undergraduate research advisor at University of Montana. The first time I ever used mass spectrometry for research was under his guidance. And Dr. Veronica Bierbaum was my PhD advisor at CU Boulder, where I also focused on mass spectrometry. So I just want to take a moment, if you're a student out there, maybe you've found a mentor, maybe you haven't, it's worth searching for one. So I would encourage you to reach out to Dr. Christine Smith, our undergraduate research coordinator extraordinaire, and allow her to help guide you. You know, what are you interested in? What department are you in? What faculty members might have availability in their research groups? Do some effort, do some groundwork to try to find someone, because science is not the kind of thing you do alone. You do it in a group, and you do it with a mentor. So yeah, go find one. Quick show of hands. Is anyone currently working for fast food, or have you worked for fast food? Yeah. Respect. That's where I started. Ponderay, Idaho, Burger King drive-thru. I had a headset just like this, but I felt slightly less cool. The most stressful day, like in my entire professional career, was when the Whopper went from 99 cents to like $1.03. And I really heard it in my headset. I heard the feedback, the negative feedback. Gotta start somewhere. So I started here, and for about 5 years, I waitressed and worked at grocery stores in the produce department. And that wasn't my dream. So when I got to University of Montana, I qualified for the Pell Grant and for the work study program. And through the financial aid office, I was able to get matched with a work study job in a lab. And not just any lab, the Montana State Crime Lab. What? So yeah, it's not like I was doing science, though. I was washing beakers and pipettes that were covered in blood and urine, but I was there. And I got to see other scientists do stuff, and I was standing near mass spectrometers, and I had no idea what they were at that time. But I was a teenager washing dirty beakers in the crime lab, and it was my start. Once I had that, I was like, okay, let's keep working in the lab. I took analytical chemistry from Dr. Chris Palmer, and afterwards I was like, can I work with you? And he said yes. So I found a mentor. And he was working on a project that really landed for me. So growing up, we exclusively used wood to heat our house. I'm curious how many of you are currently using exclusively wood to heat your house, or have you in the past? Yeah, quite a bit of us. If you have, potentially you've gotten ash or smoke in the face at one or more occasions, and that's not great. That contains polycyclic aromatic hydrocarbons and carcinogens. So Dr. Chris Palmer was interested in quantifying a urinary biomarker for wood smoke exposure, so that when you go to a doctor's office and pee in a cup, potentially that's one of the biomarkers that comes back and says, ooh, we need to have better air filtration in your home or an EPA-certified wood stove in your home to limit your exposure. I looked for levoglucosan using quadrupole mass spectrometry under Dr. Chris Palmer. in his group, and turns out levoglucosan isn't a great urinary biomarker, but negative results are results. You actually pee out levoglucosan for many other reasons besides being exposed to wood smoke. So it's not ideal. It's not particular. I graduated from University of Montana in 2010, moved to Boulder, bumped into this thing. It's gigantic. I don't know if you can tell, but so yeah, it takes up most of the room. It's called a flowing afterglow selected ion flow tube mass spectrometer. It's home built. It was in Dr. Veronica Bierbaum's lab, and I was like, what is this thing? I want to learn to drive it. And it took me a long time to learn how to drive it. This thing, if we look at the layout on the far left here, is an ion source. We could use electron ionization with an electron beam, or we could use like graphite discharge, which is shown here. The key is we made a bunch of ions. This is a quadrupole mass spectrometer where we could select an ion of interest. And then we had a flow tube where we could conduct various reactions by introducing reagents. This is just showing a hydrogen atom, which was one of the reagents we used. We could measure reaction kinetics. We could measure which products were produced at what ratios using a second quadrupole mass spec to separate out the products. So this is where I started my PhD. And we were focused on reactions related to interstellar space, planetary atmospheres, things like that. So when an astronomer detected an ion, when an astronomer detected a neutral molecule, we were like, perfect, let's see what happens when we collide them and see if we can build more complex molecules. Specifically, by the end of my PhD, I became really focused on origin of life and how potentially nucleobases, like those that make up our DNA and RNA, guanine, adenine, uracil, thymine, cytosine, might be synthesized in an abiotic environment. So starting with smaller species that have been detected, could we synthesize these? The answer is absolutely you can. But we're working on the details. In addition to the FA-SIFT, I was able to modify a commercial ion trap mass spec to do the same job. So I'm just going to zoom in on this chunk, which is a quadrupole, octupole, and ion trap. This is a picture of the instrument. And just to give you an idea of size, as opposed to the FA-SIFT, each of these is about the size and length of my thumb. And this is about the size of my fist. So there's a little line here that we use to leak in helium gas, which is just a buffer gas that helped us trap ions. It's inert. And I just modified it so that we could have ions coming in and getting trapped, and then I could leak in any neutral reagent that I was interested in to observe a reaction and monitor the kinetics of that reaction. So I did a lot of the astrobiology, astrochemistry experiments using an ion trap setup. And when you spend years writing a thesis, no one reads it, though. That's what they don't tell you. So I put it on my slide, and I tell you that it's free on the internet, and you could read it anytime you want. It's my PhD thesis. Cool. All right. So after I graduated from CU Boulder in 2015, I moved to Durango, and I started my position here. And it turns out, guess what was in the lab? Mass spectrometers, multiple of them. And so more details about my journey in mass spectrometry, you can read about it because the American Society for Mass Spectrometry featured me this past year as one of the faces of mass spec, which was cool. So I just want to send you there if you're interested in more of the details. I'm going to give you a broad overview real quick. First of all, shout out to my undergraduate research students here. Pictured on the left, Jasmine Keys. On the right, Anna McCabe, who's here tonight. We did a really fun collaboration with Ska Brewing over the last 2 years, looking at the natural products that are delivered from various hop varieties to IPAs. They were particularly interested in the aroma that was delivered by certain hops, like what citrus aromas, what floral aromas were being delivered. So these next few slides, most of them I stole from Anna McCabe's senior thesis. So let's check them out. I just want to give you an idea of what type of sample preparation might be involved before using mass spec. So another shout out to specifically Chris Kerr, Heidi Hemmetsberger, and Steve Breesley at SCA. Thanks to them, we had 4 different fermentation vessels running, our experiments, which is just like way more than I ever dreamed. We were able to have a control vessel with no hops, and then we could run a triplicate experiment with one hop at a time. So we could see our precision. Here we go into Anna's beautiful slides. So when we took a beer sample, we took about 10 milliliters of beer, made sure there's about 10 milliliters of headspace room because we were trying to monitor the aroma. We made sure to add a known quantity of an internal standard that was deuterated so we could easily distinguish it from molecules in the sample, and we just put that in a 40 degrees C water bath. Turns out that at 40 degrees C, and at any temp really, but the hotter the better, there's a non-negligible vapor pressure of volatiles above the liquid sample. And our goal was to sample those volatiles, so we introduced a polymer fiber, and an equilibrium happened where there was deposition onto our polymer fiber. We took that polymer holding the aroma molecules, and we injected it into a gas chromatograph, which obviously is not part of this talk. It's beyond the scope. Ask me later. The gas chromatograph helps separate molecules based on their polarity and boiling points. So we were able to separate out the molecules first, then they enter the lovely ion beam, or ion source, which is a beam of electrons, and then a quadrupole to separate them based on their masses and charges. After separating everything out, we get data that looks like this, where we can distinguish like the top 10 molecules contributing to the aroma of beer hopped with Azacca hops, Idaho 7 hops, Sultana hops. And it turns out one of the key take-home messages of this experiment was that for the same amount of hops, Sultana delivers increased concentration and increased variety of aroma compounds. And hops is a very expensive raw ingredient used in brewing, and people love IPAs. I personally don't, but people do. The market has spoken. So being able to choose a specific variety of hops that delivers a good bang for your buck is what brewers are really interested in. That was a little crash course from like 1996 to present in my life. Let's talk about the future of mass spectrometry in general before we end today. Shrinking mass specs. So as you might imagine, several of you are environmental scientists, I know that. If you have to do field work, please don't make it the size of an FA sift that like can't even fit in a truck. So we're designing mass spectrometers to be smaller and smaller and smaller so that they can be taken into the field and provide chemical information as needed to environmental scientists or even forensic scientists visiting a crime scene. Speaking of small experiments, Dr. Jibo Yang was a postdoc in the CU Boulder Research Group where I was a graduate student. We worked closely together for years. And this past year, we were co-guest editors for the journal Mass Spectrometry Reviews. So I just want to like toot his horn. He has designed a way to sample individual living cells, just one living cell, and sample its contents into a mass spectrometer. Using this, he can study drug delivery, he can study disease, he can study stem cells, metabolism, you name it. So far, we've been looking at aggregates of cells, and this is the first time we're able to look at an individual cell. What molecules are being metabolized at what rates. So this is a really cool experiment. He's at the University of Oklahoma. Another really interesting future application that's been worked on for decades, primarily by Dr. Graham Cooks at Purdue, is introducing real-time mass spec for a surgeon. So as they're performing surgery, giving them chemical information about the patient's tissues. This is a little video that I got at the American Society for Mass Spectrometry meeting a few years ago. You've got the mass spectrometer. It's connected directly to a surgical tool that can cut or cauterize. And as you might imagine, for surgeries, especially on the brain, we want to be sure to not remove healthy tissue. So just removing tumor tissue and knowing exactly where that line is. So as a surgeon is making a cut, it's live sampling the molecules from the surface tissue and taking it directly into a mass spectrometer. And the surgeon can watch a screen that shows whether that tissue is tumor tissue or healthy tissue based on a database that we build. So in real time, you can see that as surgery is being conducted. Maybe you're aware that we're also switching to robotics in a lot of surgery settings, or we're hoping to. At this same national meeting, I went to a whole session on chemically aware robots, and specifically chemically aware robots that can do surgery. Just gonna leave you with that terror. We're gonna just, yeah, I'm scared of it, but I'm also like, but mass spec though. They do mass spec, that's cool. This is the Rosalind Franklin rover set to launch in 2028. It's got a mass spec on it. I just wanted to show you, like, we're still sending them to Mars. Like, cool. I'm really excited about this particular mission. NASA is sending, this is called the Dragonfly mission because it's got a lot of little helicopter things and it can fly to different locations on Titan. And Titan was Saturn's moon that I talked about at the beginning that is an early Earth analog. So in 2027, we're launching this thing. It should be on Titan in the mid-2030s. Cool. Yeah, very excited. Very excited about that and the data that they get from that. Well, hopefully you learned something. Thank you for being here. Specifically, I want to thank the undergraduate research students I've worked with. Shout out to Anna McCabe for your great slides. I don't even know how to work PowerPoint compared to you. Yes. Undergraduate research program and Dr. Christine Smith, and the Department of Chemistry and Biochemistry, who's supported me in doing all sorts of weird projects that are of interest to me and my students. Also, shout out to all the science mentors out there. It's a lot of work and it's worth it, and go find yours.